Now on to light microscopes. First, let's talk about simple light microscopes. Simple light microscopes have just one lens. This will become more clear when we talk about compound microscopes. They have more than one lens. So here is an example of one of the first simple microscopes. It's constructed by Leeuwenhoek in the 1600s. Leeuwenhoek was a textiles merchant. When he was inspecting the fabrics, he needed close-up lenses, or he needed magnification, so he would grind his own lenses. And he became very interested in what he was seeing microscopically, and he made microscopes that were smaller and smaller. So here's the specimen holder, there's the lens. He would hold it up to the light with his eye on the other end and would see what was on the microscope. Let's move on to compound microscopes. Compound microscopes are generally what we use, and here's a picture of a compound microscope like what you've been using in lab. Compound microscopes are called that because they have more than one lens. So here, going from the specimen up, we have our first set of lenses called an objective. In this case, it looks like we've got 4 of them. You start with low magnification, go up to higher magnification, and up here we have the ocular lenses or the eyepieces, which re-magnify the image that comes from this lens. Whatever magnification we have here, we multiply the magnification of the objective that you're looking at by the magnification of the ocular to get your total magnification. Now, because light is going through multiple lenses, you need to have skill in lens grinding, because if you have a defect here, it's going to show up here and it's going to be even bigger. Whereas with the simple microscope, if you have a defect here, it's not quite so obvious. Now, this is a bright field microscope, like what you've been using in lab, where the background is bright and the object that you're looking at is darker because it's blocking the light. A dark field microscope, on the other hand, has a dark background and the specimen itself is light. Now, you can go ahead and read through this, but basically what it's saying is, because of this dark field stop that's on the condenser, light is sent at angles. Now, if it doesn't hit a specimen, now remember, light bends when it hits something of a different optical density. If it doesn't hit a specimen, it's not bent and it is scattered or bent past the objectives, and you don't see that light. Whereas if it hits a specimen, then the light is bent into the objective lens and the specimen appears light against a dark background. This provides contrast without staining. So let's take a look at what this would look like. So here is an example of a bright field microscope with a eukaryotic cell that has not been stained. So you can see the things that are denser are darker because they're blocking more light. Here's the same specimen with a dark field microscope. You can see that the denser areas are brighter because more light has been bent into the microscope and we have a dark background. This one's easier to see without staining than this one is. Why would we worry about whether we stain something or not? Generally, stains kill what you're staining. So here we can observe live cells and cells that are delicate, that can't put up with staining. It would change their shape or their size or something along that line. So let's talk about a phase contrast microscope. Phase contrast does more manipulation of the light. But basically what happens is, light that passes through something with a different optical density is slowed down. The more dense it is, the slower it gets. Basically, in most specimens, light passing through a specimen is naturally a quarter out of phase. So we're talking the crests and the troughs of the light. So what we do is we put a filter in that slows the light down, slows it down by another quarter phase so that it's half phase. So why are we doing all of this? So that you can get contrast, so you can get shadowing. So let's take a look at this bright field microscope. Very unsatisfactory, makes you feel like you had to put a stain on it. Here is a phase contrast. Isn't that lovely? Because we've messed with the light, we get shadowing, and it's easier to see things. So here's the phase contrast. Now we can mess with this even more and use a phase differential light microscope or a Microscopy. We get a 3D image. Isn't that lovely? A lot of times when you're watching TV shows and they're showing how they're injecting DNA into a eukaryotic cell or something along that line, they're using the Microscopy microscope so that we can look at live cells without staining them and get a nice 3D image here. Let's move on to the fluorescent microscope. Some molecules absorb light and reflect energy back at a longer wavelength. We'll talk more about that when we talk about photosynthesis. They glow. Molecules glow when you expose them to light. So if you've played with glow-in-the-dark toys when you were younger, it's this principle. You put them in visible light, and then when you turn off the lights, then they release light at a different wavelength, usually that greenish yellow glow. So we make use of this with light microscopes. There are some organisms, Pseudomonas aeruginosa, and chlorophyll that naturally fluoresce. So we can put a light on them and they will glow and you don't have to stain them. Those are only two organisms if you want to think of the chloroplast as being a separate organism. So what we do is we get molecules that naturally do this and use them to stain. So there are some fluorescent stains that are specific to different organisms. So we have this isothiocyanate that specifically attaches to Bacillus anthracis, which was very useful during 2001 during the mailing of the spores. There's this one that's naturally attaches to tuberculosis. So let's take a look at when this would be useful. So here's a light microscope. This is some bloody sputum. Sputum is the thick mucus that we get from the lung. Cough it up. It's bloody. You can see the red blood cells in there. We're checking this patient for tuberculosis. They have bloody sputum coming up when they cough. That's an indication that they are in late phase tuberculosis. But I don't see any bacteria in there. And if we were to stain this, say with an acid-fast stain, the stain would get caught in the sticky mucus. So if we apply a fluorescent stain that's specific to the bacteria, oh, look at all of those cute little TB bacilli. Not cute for the patient, but it shows up nicely with the fluorescent microscopes. So you can see that a stain that's specific for what you're looking at would be of use. But so far we've only talked about 4 organisms that we can use with this. We've got the naturally fluorescing ones, and we've got the ones that we have stains that are specific to them. So what do we do for everything else? Well, we use immunofluorescence. The immuno are antibodies. Antibodies are produced by your adaptive immune system. We'll get more into that into later chapters. But antibodies are specific for certain proteins, and they will only attach to certain proteins. So we take antibodies that are specific to proteins that are on the surface of our cute little bacilli here, and we attach a fluorescent dye to the antibodies. Then when we put the antibodies into a sample, they will only attach to what we're looking for. Isn't that wonderful? We use immunofluorescence more than we use autofluorescence or the stains that I mentioned that are specific to anthracis and M. tuberculosis. Now, confocal microscopes take advantage of immunofluorescence and kind of raise it to the next level. So basically, you have a very small opening and you can take pictures as you move up the specimen. And it's kind of like a CAT scan. And you get these lovely 3D images, especially if you attach different fluorescing molecules to different antibodies. So here we've got a sand granule, we've got a fluorescent antibody that's specific for a specific polysaccharide, We've got some that are specific for a specific bacteria. We've got another one that's lighting up pink. We use this when we're looking at complex communities of bacteria. In other words, this is a biofilm, and we're looking at the structure of the biofilm using the 3D image that has been generated by the confocal microscope.